Consider a system where we have a mass in the xy plane that's at a distance r from the origin. It's drawn here on the right-hand side. Now its segment to the origin also makes an angle of phi with the x-axis. And what I want to do is imagine that the mass, the distance from its origin, is fixed, but it's moving around in a circle as drawn here, this red circle. So in effect what's happening is the mass is rotating in the plane. How would we describe the motion of this? How would we write down its energy? Well, we might start by writing the energy as 1/2 mv squared. And since it's in the xy plane, we could further break this down and write this as 1/2 mvx squared plus vy squared. And if we wanted to be really mathematical about it, we could even write this as 1/2 m times the derivative of the x coordinate with respect to time squared plus the derivative of the y coordinate with respect to time squared. And all of this would be perfectly great. I should mention too that this particle has no potential, so it's only kinetic energy that's going on here. As it turns out, though, for rotational motion, Cartesian coordinates are not really ideal. So what we want to do is we want to re-express these coordinates in terms of plane polar coordinates, which means we would define our x to be equal to r cosine phi, as it is here, and y is equal to r sine phi. Now, if we want to rewrite our kinetic energy term here in terms of these new coordinates r and phi, what we're going to have to do is to take our time derivative and use the chain rule to rewrite it in terms of r and phi. So, for example, I might write this as the dr dt times cosine of phi. So in other words, I'm just taking the time derivative of this plus d phi dt, and actually it's times minus sine of phi here, which would be the derivative of cosine of phi. And I need a factor of r there in front. Now, I don't have any motion in the r direction. In other words, r is staying fixed, so this has got to be 0. So that leaves me with this as my final result, or perhaps I should write this as negative r d phi dt times sine of phi. Now I would do the same thing for the y coordinate, and if I went through that same analysis, I would end up with the result that dy dt is equal to r times d phi dt cosine of phi. So now when I take the square of this to represent that, and the square of this to represent that, I can now write my energy in terms of r and phi as follows. I'll have 1/2 m times this quantity squared, which will give me r squared d phi dt squared times sine squared of phi. And this thing squared, the second term, will be plus r squared d phi dt squared times cosine squared of phi. Now you'll notice that I've got these terms are the same for both of these, and so I just have sine squared plus cosine squared. I hope you remember enough trigonometry to know that sine squared plus cosine squared of any angle is always equal to 1. So that means that my final expression for the energy is going to be 1/2 mr squared times d phi dt quantity squared. Now this is a perfectly adequate way of writing this down, but it turns out that it's a little awkward to be writing this as a derivative with respect to time. So what we do is we define this derivative as an angular velocity called omega, just like the omega we use for the harmonic oscillator. So we in fact rewrite this as 1/2 mr squared omega squared like this. This omega has units of inverse seconds or radians per second. And when it's multiplied by mr squared, it gives us something with units of energy. Now the mr squared is another quantity that we run into a lot when we have rotating bodies. We refer to this as the moment of inertia, and it is a term that includes not only the mass of the particles, but their distance, if you will, from the center of rotation. In this case, it's the center of the coordinate system, so that r functions as that center. We give it a special symbol. We call it I is equal to mr squared. And so we can rewrite this expression for the energy now as the moment of inertia times the angular velocity squared. All right, which now is an equation that you may have seen in your physics course or in a physics textbook. All right, and this is a perfectly good way of expressing the rotational energy of a particle like this in the plane. Now, remember that in linear motion, we can define a momentum as equal to a mass times a velocity. All right, so this is linear motion. Can we do the same for rotational motion? Well, in fact, we can. The analog to the mass is, of course, the moment of inertia, and the analog to the velocity is the angular velocity. So if I take the product of those two terms, I end up with something that I'm going to give the symbol L, and this L is the angular momentum. So this was linear momentum up here. This is angular momentum down here. And angular momentum is really the central quantity that we're going to be dealing with throughout this whole module. All right, angular momentum is defined this way when we have simple rotation in a plane. But if I were looking at rotation in three-dimensional space, I would actually define the angular momentum as a vector. And it's a vector that's equal to the vector that describes the location of the particle relative to the center of rotation with a cross product times its momentum. Now, I want to be clear about this. This cross product is a special product that combines two vectors, and it results in a vector itself. So sometimes it may be written like this. I'd have x, y, z as my r vector, and I'd have a cross with px, py, pz, where what I'm doing is I'm listing the components of a vector in vertical array. All right, we'll talk a little bit later about the definition of this cross product in case you're not familiar with it, but I want you to be aware that angular momentum is in fact a vector quantity, and when we write things like this, we're really talking about the magnitude of the angular momentum. Now, one last thing, I've written down our energy as I omega, 1/2 I omega squared. All right, now if I solve for omega here, omega is equal to the angular momentum divided by I, so I could write this as 1/2 I times the angular momentum over I squared. And when I work all of this out, I'm going to end up with 1/2I times the angular momentum squared. And in fact, this is the operational definition that we're going to have for rotational energy or energy due to angular momentum in our subsequent lessons.